Okay, good afternoon. I'd like to thank the organizers for organizing such a wonderful workshop and giving me the opportunity to talk today. So this is joint work with Jingu Kim, who was my PhD student and postdoc, and now with Nokia, he's here, and the two other PhD students, Da Kwang and Yoon Long Hee. So non-negative matrix factorization has been around for now almost 20 years. And during those 20 years, there has been tremendous amount of research results produced around non-negative matrix factorization. So in this talk, I will focus on algorithms and some applications. And since there are so many algorithms, I cannot cover all of them, but I will show you that some of the most promising non-negative matrix factorization algorithms can be explained using one framework from optimization, which is block coordinate descent framework. And it has nice convergence property that we can take advantage of. And then I will show you some other algorithms. And then I'll show you some variations of non-negative matrix factorization. Here I will focus on NMF formulated using Frobenius norm. And tomorrow during the poster session, we have fast NMF using Bregman divergences. That's joint work with my student Liang Dali, who is here too. And NMF has been used especially in a successful way for clustering. So I want to offer some conceptual understanding of why NMF works well for clustering, its shortcomings and advantages. And NMF can work as a clustering method when we have sparse NMF, and then now we want to propose a new formulation which we call Symmetric NMF. Okay, so let me first define the problem. So given a non-negative matrix A, so NMF can be defined for any matrix, but it makes more sense when the matrix, so here I assume matrix is data matrix. Data is encoded without using any negative component. So A is non-negative, and suppose the desired rank, so this is a reduced rank, so we assume that this is much smaller than M and N. Rank K is given, then we want to find the two factors, non-negative factors, W, which is M by K, and H is K by N, so that A can be approximated well by the product of these two non-negative matrices. So depending on what we mean by A can be approximated well, okay, we can use a difference measure. And here I will focus on Frobenius norm-based minimization. So the problem can be formulated this way. And this problem is not easy because it's not convex. So only A is given, K is given, and we have to find both W and H. So non-convexity makes the problem difficult, and W and H are not unique. Suppose you find one W and H pair, and then suppose you find another non-singular matrix X or D, so that WD is non-negative and D inverse H is also non-negative, then that's another solution pair. So how do we find these? Okay, so, but we can show that as far as we didn't quite reach non-negative rank, then as we increase the reduced rank, then we can have strictly better approximation as we find another non-negative matrix factorization. But if the lower rank approximation, finding the best lower rank approximation is the goal, then why do we use NMF? Because theoretically we know that SBD does the best job. Right? So suppose the measure is Frobenius norm or L2 norm, then we cannot beat SBD. So NMF residual will be always at least as large as SBD, but NMF offers some other advantages. So for non-negative data, it offers a better interpretation of the result. So I will tell you more about what we mean by better interpretation. So this is the overview of algorithms. And most notable algorithm is multiplicative updating rule by Lee and Sung. That was presented in Nature. And even now, I think that's most commonly used NMF algorithm. So I'll talk a little bit more about that. And then after several years, Michael Berry and others presented alternating least squares algorithm. So that offers a different paradigm shift. So here it's alternating least squares. So because non-negativity is expensive to impose, they just consider the problem as if there is no non-negativity, and if there is negative component produced in the solution, they just set them to be zeros. So the goal there was locally find the fast solution, but because of that fast part, actually it suffers from lack of convergence. So later people found out that although it is expensive locally, it is important to impose non-negativity explicitly. So those algorithms are called alternating non-negativity constraint least squares, also ANLS-based NMF algorithms, and there are several algorithms. And I will also talk about this hierarchical ALS, and that same algorithm as this one. And these two algorithms are now one of the fastest algorithms. Okay. And algorithm research is very active. So just last year and this year, there are even better algorithms produced. So I'm not going to compare all those algorithms, but I will just show you some bigger picture. So what is block coordinate descent method? So by using this BCD framework, the goal is I want to explain many promising NMF algorithms. So in constraint nonlinear problem, we have a function that we want to minimize. In NMF case, this is the function. And the unknowns can be partitioned into P blocks. Okay? So if that's the case in block coordinate descent method, we fix everything else except for variables in one block, look for the solution, and then we iterate. So if we do that, there is nice convergence property by Berzickas. Okay, suppose f is continuously differentiable, and it's over Cartesian product of closed convex sets. Okay, so non-negativity, so it's bounded below by 0, and then we can put some gross upper bound. So we can make those convex. And suppose for each subproblem, we can uniquely find the solution is unique. So unique solution is attained. Then the results shows every limit point of the sequence is a stationary point. So that means when it converges, it will converge to a local minimum. And since the problem is non-convex, this is really what a good algorithm should achieve. And there's an interesting result by Grippo and Ciandron showing that when the block is only 2, then this uniqueness is not required. Okay, so as far as we find solution for each block, then altogether we can achieve that every limit point is a stationary point. Okay, so now going back to NMF, what does it mean? So we have A, and we want to find W and H. So let's have one extreme case. Let's just say everything else is fixed and we just don't know one component in W or one component in H. So suppose this is unknown and then we fix everything else and we look for it. And we can do the same for any element in H. So if you write that this way, then you can see that the problem is simply just quadratic function minimization problem, where here Wij is unknown and Hij is unknown with non-negativity constraint. So we can find the closed form solution, and actually this can provide a good framework when you do NMF with Bregman divergences, because unlike other than the Frobenius norm, other Bregman divergences does not give us much room to do algebraic manipulation. But using this framework, we can design fast algorithms. Okay, so how about multiplicative updating algorithm? It looks like this, but if you rewrite it in this gradient descent form, it looks like there's this current one, and then there's a negative gradient, and it's choosing this step size. And if we write our scalar coordinate descent method, then this is the solution, and this plus means if this solution is negative, then we just set it to be zeros. So this allows us to compare these two, and then we can see that this multiplicative updating algorithm, they use conservative steps so that non-negativity is always imposed. Okay, so what I want to emphasize is this multiplicative updating algorithm does not use block coordinate descent framework, so that convergence property we have is not applicable. So in their original paper, they say their algorithm converges to local minimum, but later it was found out that that is not the case. It's just the objective function does not increase as they iterate. So next natural way to partition the unknown is by blocks. So we will partition W into columns and H into rows, fix everything else, and look for either one column of W or one row of H. So if we write it in this way, then inside we need to iterate solving this kind of problem. So the general form of this kind of problem, okay, simplifying, deleting all these indices, it looks like this. So it's non-negativity constraint least squares problem where there is only one vector. C is not a matrix, it's just one vector, and then there are multiple right-hand sides. And what's nice about this problem is, okay, if we don't have non-negativity constraint, then this is the usual least squares problem, and we know how to find the solution. We can just use normal equation, for example. So C transpose C, X transpose should be C transpose G. So X becomes like this. But now there's non-negativity. But what is interesting is, okay, we find this X as if there's no constraint. And if X has any negative component, just set them to be zeros. And that's not just ad hoc fast solution. That is really the solution in this case. So each sub-problem has closed form solution. Okay, so this iteration was proposed as hierarchical alternating least squares and rank 1 residue iteration by two different groups independently. So here, because I'm talking about vector iteration, I want to say something else which is related, which is about successive rank 1 deflation in computing singular value decomposition or non-negative matrix factorization. So using Perron-Frobenius norm, what we can say is if we have a non-negative matrix, then its leading left singular vector, right singular vector can be found so that they are completely non-negative. Okay? So because of that, if we are doing rank 1 reduction, then SVD is the same as NMF. Okay, so can we take advantage of that in algorithm? What about rank 2? And unfortunately, from rank 2, it's not that simple. It's not only not that simple, it can be misleading. So here, I want to emphasize that when we compute the singular value decomposition, we can use a successive rank 1 deflation. So what that means is, give me a matrix A, non-negative matrix A. I find its best rank 1 approximation, SVD, best rank 1 SVD, and subtract that influence, and then to the residual, again, I do best rank 1 approximation, and then I keep doing it and put them together, and that will be the answer. But that's not the case in NMF. You cannot do successive rank 1 approximation. First of all, A might be non-negative, but after first step, this residual matrix is not necessarily non-negative. So we cannot necessarily find non-negative vectors that are like SVD. Okay, so here, this is just a counterexample. So suppose you have a matrix A like this. It happened to be symmetric, so SVD is same as symmetric eigenvalue decomposition. And if we do two successive best rank 1 non-negative approximation, then first we will find this, okay? And then subtracting that, then the next rank 1 non-negative approximation is that. So altogether, this is the best rank 2 approximation. But really, the best rank 2 non-negative approximation looks like this, and this gives the better residual, smaller residual. So we cannot go this way. So in case of NMF, you cannot find certain vectors and then say those are final, and then just to look for the rest. If you are doing rank K approximation, you have to find the 2 K vectors, K in H and K in W, all simultaneously. Okay, so 2K vector block coordinate descent method, which is HALS and RRI, that's different from successive rank 1 deflation for NMF. Okay, now this is really the most natural partitioning of NMF into blocks. We don't know W, we don't know H, so let's say W is 1 block and H is 1 block. Okay, so let's fix H and then look for W. So this is non-negativity constraint least squares, multiple right-hand side, and we need to find multiple vectors. And then now this time W is fixed, so we solve this problem. So inside, this is just non-negativity constraint least squares problem with multiple right-hand side. Okay. So at the high level, it looks like, yes, these problems are simple, but now when it comes to solving these sub-problems, it's not easy. Now there's no closed form solution. Okay, so many different algorithms, they are actually based on how we solve these non-negativity constraint least squares problem with multiple right-hand sides. Projected gradient, projected quasi-Newton, And then there are active set-based methods. So I briefly mentioned this ALS, non-negativity constraint least squares. So ignore this non-negativity, just solve least squares problem. So here, suppose W has any negative components, just set them to be zeros. Okay, so problem is formulated as non-negativity constraint least squares, but solution is not. So it might be a quick approximation for the solution, but it suffers from sometimes non-convergence. Okay, so this is the sub-problem, and B, the columns are not related, so we can separate the problem into some of these problems. And in solving that, these methods, okay, they find good initial guess, and then theoretically, as you iterate infinitely many times, it goes to the solution. But active set-based method is a little different, and these are the methods that we proposed. So we propose active set-based method, and in active set-based method, the active set, passive set partitioning is done, and then the indices are changed very carefully so that eventually we find the right active passive set. And in the process, usually the index is switched by just one, so it's often very slow. So we came up with the block principle of pivoting. This is a greedy way, and eventually it finds the right active set, passive set partitioning. And also this active set type method, it fully exploits the structure that there are multiple right-hand sides. And the problem is also very long and thin. So this is just conceptual explanation of how active set-based method works for this simple non-negativity constraint least squares problem. Okay, suppose you know the solution. Okay, you don't know the solution, that's what you are looking for. But suppose you know the solution, and it turned out that these three components are strictly positive, and these two components are zero, then that solution will be same as from the matrix, I just extract column 1 to 5 and solve unconstrained problem, find these 1 to 5 components, and then those solutions will be strictly positive, put them in, and then the rest we just set them to be zeros. Okay? So really the problem is where in the final solution in vector x are the components 0 and other components are strictly positive. So that's what active set-based method is looking for. So it's guaranteed to finish infinite number of steps. Okay, so here I will show you some comparisons. So this is alternating non-negativity constraint least squares based and block principle pivoting. So that's the method we proposed in 2008 in ICDM, and then again it appeared in 2011 in Siam Journal on Scientific Computing. And earlier we proposed active set-based method, and this is projected gradient-based. It's projected, I think this is quasi-Newton method, and Haesun and multiplicative updating, and ALS. So we did extensive comparison, and I will just show you some results. And because these are all iterative methods or active set methods, depending on what stopping criteria we use, we can have a very different relative performance. So instead of using stopping criteria, what we did was, okay, we ran every algorithm for a certain number of time, okay, and then we check what the relative residual value is. Okay. So this is text data. Dimension is like this, and because this is text data, the matrix is very sparse. So you'll see that when K is small, actually most algorithms do very well. They quickly achieve the smallest residual, but here the projected quasi-Newton method was a little slow, but eventually it achieved the minimum. And now it's the same data, but K is larger. When the reduced dimension is larger, it becomes difficult problem for most algorithms. So again, Haesun and block principle pivoting method, they did comparably, they did the best. And here's multiplicative updating, and then here's ALS. Okay, so that quick fix locally, it doesn't really help globally. By the way, I'm not showing you the active set-based method because compared to BPP, it's almost always slower. Anyway, their performances are pretty similar, so it's skipped on this slide. Now this is image data. So it's image data, so the matrix is not sparse. And this graph is when k is 80. This graph is when k is 160. And again, you can show that our algorithm, you can see that ANLS, BPP, and Haesun are the two fastest. And here, these are the two fastest. And sometimes multiplicative updating method can be very slow. So depending on how you view it, actually these algorithms perform dramatically differently. So suppose you want to finish your algorithm, any algorithm, when the relative residual is 0.2, then BPP will finish after this, and Haesun will finish here, but multiplicative updating will run for quite a while. Okay, these can be easily extended when we do non-negative tensor factorization. There are many variations that extends SVD to tensor. And here, let me just concentrate on the easiest one. This is parallel factorization. So suppose you have three-way tensor, and when we do rank k reduction, we want to express the tensor as a summation of k rank 1 tensors. Okay, so that's PARAFAC, and we impose now non-negativity in all these vectors. Okay, so if tensor is order q, for example, instead of two subproblems that occurred in ANLS framework, we have to solve q subproblems, and each subproblem is actually very long and thin because we flatten the tensor. So matrices are longer and thinner, and that is actually ideal for ANLS for BPP. It's designed to work well in this situation. So for tensor, we compared ANLS block principal pivoting, ANLS active set, and Haesun and multiplicative updating by Welling and Weber. And we saw a similar trend. Okay, so this is extended Yale face database, so 168 by 192, that's each image, and then there are 24 images. Okay. So we did rank 60 reduction, and both Haesun and ANLS BPP, again, they are, these are both active set type algorithms, and in this case, Haesun was a little slower, and this is multiplicative updating. Okay, so in this case, Haesun was a little poor initially, although eventually it converged to the same value. So that's the general trend that we saw. Okay, so now I'm coming back to this main part of the talk. So in many problems, okay, so in many applications, actually NMF worked well. NMF is shown to work well as a clustering method. So is NMF related to K-means? Okay. There are papers showing NMF is equivalent to K-means, and I want to say it depends on what you mean by equivalent. It's not really equivalent. Okay, so first, the clustering and lower rank approximations are related, right? When you do clustering, okay, after clustering, you have cluster representatives. For example, when you do K-means, these centroids are there. So you can say, when you put those centroid vectors together, that's the new basis in your k-dimensional space. And then there is a cluster membership indicator matrix. So you can say that's the k-dimensional representation of your original data. Okay, so that way, you can view clustering as a very special case of lower rank approximation. Okay. That becomes clearer if you look at the objective function for K-means and NMF. Okay? So this is the K-means objective function. So AI is the data point. There are n data points. And we want to find the cluster structure so that each W sigma I is the cluster centroid. Okay, earlier in our paper, we say, okay, that can be written in this way. So after it's written in this way, it looks like NMF. But I want to tell you that there is some very subtle difference. Okay, so in K-means, if you write K-means this way, then columns of W are K cluster centroids, and columns of H, HI, those are cluster membership indicators. In NMF, W, the columns of W are new basis vectors for rank K approximation, And H, the columns of H can be viewed as a k-dimensional representation of A. So in NMF, if we put additional constraint that these columns of H should be EI, some columns of the identity matrix, so that they behave like cluster membership indicator matrix, then NMF can behave like a clustering method. Okay. So to achieve that, we designed a sparse NMF. So what we do here is we impose a sparsity on the second factor so that they behave, so the second factor behaves more like cluster membership indicator matrix. So to do that, okay, we have this formulation and we put one norm. So one norm makes columns sparse, and then we put square term here. And because we have this one norm based regularization on H, some components will become 0. And because of that, W can blow up. So we have regularization term on W so that W does not become too big. So if you look at this formulation, actually because of this one norm, it looks like algorithm will become more difficult. But in this case, because of non-negativity, one norm does not make algorithm more difficult. It's still differentiable because we are only dealing with positive orthant. And not only that, if you use alternating non-negativity constraint least squares framework, okay, so suppose W is fixed, then it's WH minus A, WH minus A. W is fixed, so this disappears, and then there's H, and that H can be taken care of like this. This E1K is vector with all completed ones. Okay, so by having this row with all ones, we are actually adding up the columns of H. Okay, so that takes care of that. And then if now H is fixed, then this term appears here. Then H is fixed, so this disappears. And then this term, we can just put identity matrix, so W gets also minimized. So after we have this formulation, then we can just simply use alternating non-negativity constraint least squares problem. Okay, so I showed you that K-means and NMF are related, but the fact that the objective function of NMF can be modified so that it looks like K-means objective function, it doesn't mean that those algorithms behave in a similar way. So here the subtle difference is the purpose of clustering is separating the data points into groups so that those data points belonging to different groups are remote, and within each group the data points are closely related. But the purpose of low rank approximation is really to approximate A best using these low rank matrices. So implicitly, W will be achieved with linear independence in its columns. Okay, so I think in the next example will make that point clearer. Okay. So according to many papers, it has been shown that NMF performs well on documents. So what is so special about documents? Okay. So in case of documents, the columns of these new basis vectors, okay, they are good cluster representatives for documents. And we also did some implementation. So this is TDT2 text data. And these are number of clusters. And we ran each method 100 times with initialization by random matrices. And these are the clustering accuracies, K-means, NMF, and sparse NMF. And overall, NMF-based method worked much better. And as dimension goes higher, actually, the performance of NMF-based methods become better relative to K-means. But, okay, so does it mean that NMF and SNMF can be used as a clustering method? But this example shows that actually NMF can fail as a clustering method. So here in this graph, what is important is the origin is here, okay? And suppose there are these two data clusters, one red one here and one blue one here. If you run K-means here, the cluster separation is clear. It's not a difficult problem. You will find this separating hyperplane easily. But if you run spherical K-means, then the distance is based on cosine measure. So it's not going to separate the groups into this and that. It's going to separate the groups to this and that. Okay, and then now if you run NMF, then it will also find the separating hyperplane which goes through like this. And the reason is NMF, when you do rank 2 approximation, it's going to try to find 2 linearly independent cluster representatives. And here the assumption is, okay, we generated this artificial data, so the first cluster centroid is here, and then the next cluster centroid is here. They're same vectors, so they're linearly dependent, and NMF cannot find it. Okay, but NMF still approximates the data points well, but no 2 basis vectors can represent these 2 clusters in NMF. So it's because NMF tries to find, in this case, 2 linearly independent vectors representing 2 clusters. So you will find these 2. Okay, so what we find out is NMF is not really behaving like K-means. It's really behaving like spherical K-means. When the distance measure is not Euclidean 2 norm, but it's cosine measure, then NMF and the spherical K-means, they behave very similar. And I think that's the reason why NMF has been very successful on documents, because on documents, we usually normalize, and then we try to find the trend. So typically, it's really inside, the cosine is used as distance measure. Okay, so now what we want to do is we want to generalize NMF so that it can deal with nonlinear structure, so that it can behave like spectral clustering. So that's what we call by symmetric NMF. So now I'm proposing this symmetric NMF as a general graph clustering method. So what's the motivation? If H is a cluster membership indicator matrix, so it's non-negative and H transpose H is identity, then this is usually the objective function that appears in graph clustering. So it depends on what S is. This is a similarity matrix. Oh, okay. Similarity matrix. So depending on how similarity matrix is formed, you will have a different graph clustering algorithm, but it's formed this way, but under this condition, that is same as this problem, where S is the pairwise similarity and H is the cluster membership indicator. And in spectral clustering, what they do is they relax this condition. Okay, ignore non-negativity, just keep this, and then spectral clustering becomes just solving for this problem with H transpose H's identity. So we find leading eigenvectors or eigenvectors corresponding to the smallest eigenvalues, and then do K-means clustering at the end. But now what we propose is, okay, instead of that, now we give up this orthogonality. We'll just keep non-negativity, and then that's symmetric NMF. So spectral clustering relies on eigenstructure of S. So depending on eigenvalue separation, it may work, it may not work well. But solution of symmetric NMF, it's independent of eigenvectors. We don't compute eigenvectors. We just find this H, which is non-negative. And how does it work well? And then we don't do post-processing. We don't do K-means clustering again. We just use H as a cluster membership indicator matrix, and then just find the largest component as a cluster membership. So this is conceptually explaining what's going on. Suppose this is the similarity matrix, and these pink data points are very closely related, and white ones are not closely related. So there are 2 clusters. And now if we run this symmetric NMF, it has to find rank 2 symmetric approximation in this way. So when you put them together, it naturally reflects the cluster structure. Okay? So this kind of formulation was used earlier, but in that case, it was the kernel extension of NMF. So S was a kernel matrix. So earlier, S has to be symmetric positive semi-definite. Here, our S can be any similarity matrix. So it's indefinite. And in that case, multiplicative updating rule does not work. And we have developed a new algorithm to achieve that. So now I don't have much time left. So let me just quickly show you some results. So these are artificial graphs. And we ran many different spectral clustering algorithms. This one is by Ng and Jordan and Weiss from NIPS 2001. So number of optimal assignments among 20 runs. So symmetric NMF worked much better. And this is Reuters data and cluster accuracy. We compared K-means, NMF, and graph regularized NMF, spectral clustering, and symmetric NMF. And especially as K goes larger, symmetric NMF worked significantly better. Okay, and similar result when we did object recognition. This is a 20 cluster problem, and symmetric NMF worked better consistently. And now we are applying this for image segmentation. So there are results using spectral clustering for image segmentation. So instead of spectral clustering, we use symmetric NMF. So this is the original image, and this is symmetric NMF segmentation result, and this is spectral clustering, and same here. And it seems that spectral clustering finds more spurious, incorrect segmentation results. Okay, now to summarize, I gave you the overview of NMF algorithms when Frobenius norm is used. And I showed you that by using block coordinate descent framework, many successful, so fast and convergent NMF algorithms can be explained, and it can easily be extended to tensor case. And for clustering, we can use sparse NMF, but they are not necessarily a clustering method. And we propose symmetric NMF for graph clustering. So what kind of work is left? I think one advantage of NMF for clustering is because it's already formulated as optimization problem, so semi-supervised clustering becomes easier. So they just become more constraints to add. And NMF can be used very successfully for probability-related methods because the values we compute are non-negative, so they can be easily interpreted as a probability. So we are working on relating NMF to latent Dirichlet allocation. And then we have adaptive NMF. And now we are doing NMF implementation for really large scale problems by doing GPU implementation and also NMF with other difference measures, okay, we are using. So in conclusion, what I want to say is all these are done, but one thing really which is still remaining as a mystery is, earlier I told you that NMF is not unique. The two factors we compute, they are not unique, but in many applications, we compute NMF and then take one factor, say second factor, and use it as cluster membership indicator and so on. So how is it working well, although they are not unique? So there is some more theoretical study to be done. And the algorithms I presented, the MATLAB codes are available on our webpage. And these are the papers that are related to this presentation. Thank you.